If you have any questions, you can put in the chat. Okay, so we'll start today's lecture on microwave engineering. So today we are going to continue the section on transmission lines, and specifically we are going to be talking about lossless transmission lines. And then also we are going to talk about the different, terminations that can happen at the end of the transmission line, and based on the termination type, such as open circuit, short circuit, how the impedance is going to vary along the transmission line, right? So based on those derivations, we can actually we can decide what is the impedance of a transmission line at a certain location, and based on that we can connect another circuit to the transmission line, such that such that we can transfer maximum energy to the transmission line from the input circuit, right? So in order for us to do that, we need to calculate the impedances along the transmission line, and therefore we need to consider how we can mathematically denote that impedance using a equation. So we'll be talking about that in this lecture. So transmission lines, right? So I have told you there are two types: lossless transmission lines and lossy transmission lines, right? So lossless transmission lines means that the attenuation factor, or the alpha, is 0, right? So this is the assumption that there's no attenuation of the wave inside the transmission line propagating over a long distance, right? So in normal conditions, you face some attenuations. I mean, the wave is facing some attenuation, but in high frequency circuits, most of the time, the attenuation is kind of negligible, and therefore we take into assumption that the transmission line is a lossless transmission line, right? So therefore, lossless transmission type is very popular when we are modeling transmission lines and when we are trying to find the condition of a transmission line. Then we also have these lossy transmission lines. That means that the attenuation factor is not 0, or it is not close to 0. It is big value. Attenuation of the wave along the line. So because of that, we need to consider some different assumptions, and we need to consider that this alpha not equal to 0 in our calculations to derive the impedance along the transmission line. So in that case, the alpha is not equal to 0. So therefore, we need to take into consideration about the value of alpha affecting the propagation constant, right? In the last class, we learned about the propagation constant being equal to alpha plus j beta, right? So I hope you can remember that equation, right? In the last class, I think you can remember. So gamma is what I used to represent the propagation constant, and it is equal to alpha plus j beta, right? In lossless conditions, we can take alpha equal to almost 0, right? So alpha equal to 0 in perfect lossless condition, and if it is like nearly lossless, also we can consider alpha is 0. So in that case, we have gamma equals j beta. Otherwise, if it is a lossy case, we need to consider the alpha plus j beta as the propagation constant. So therefore, the effect of alpha is there in each like parameter we are considering in this, right? So we are considering the, characteristic impedance of the line, even that is getting affected when the alpha is not equal to 0. That means when the line is lossy, right? So now actually in this lesson, right, we are talking about lossless transmission lines, the case where alpha is equal to 0. So when alpha is equal to 0, that means that lossless transmission line condition is there. So in the lossless transmission line condition, we took into the assumptions that R, or the series resistance value along the line, is equal to 0. Then we took the parallel resistance, so the conductance is equal to 0. That means like when the wave is propagating along the line, the resistance, the series resistance towards the wave propagation is almost negligible because it's a very good conductor, right? The amount of resistance is kind of negligible when you consider in comparison with the inductance that is generated in the transmission line when the current is conducting along the line. And then we have no dielectric loss. That means the dielectric loss that happens when there's a stray current flowing from the top conductor to the bottom conductor. So if there are stray currents, the value of G will be some value. But in this case, we are considering a case where we don't have much dielectric loss. That means the stray currents across the two conductors in the transmission line is almost negligible, and therefore the dielectric is almost a very good, perfect dielectric, a very good dielectric, right? So it does not conduct current between the two conductors, and it prevents stray currents occurring, right? So we are considering a scenario where we have good conductors and good dielectric material in the transmission line. And then we have the characteristic impedance, which gives us how much of an impedance is there for the wave to propagate from one point to another, right? It also indicates how much of energy we can transfer from one point to another point in the transmission line. So if the characteristic impedance is high, then the ability to transfer energy from one point to another point in the transmission line is low, right? So if the characteristic impedance is low, that means we can easily transfer energy from one point to another point in the transmission line, right? So when it is lossless transmission line, we have derived earlier that is Z naught is equal to square root of L over C, right? So these lossless lines, are like in the lossless lines, the characteristic impedance is characterized, the impedance, characteristic impedance is mainly governed by these L and C values. So if you know the value of L and C, you can directly find the characteristic impedance, right? And then we have the voltage and current in phase in the transmission line when it is lost. So there's no phase shift between the voltage wave and the current wave in the transmission line. So which is a very good advantage for us because we don't have to consider the phase shift between the voltage and current. They are both in the same phase, voltage and current waves. And then we have the propagation constant, right? The propagation constant is given by gamma equals J beta. So in here, the alpha is 0. So because of that, only J beta term is remaining. Right? So when we talk about the beta value, we have model it as omega square root LC. Right? And then wave velocity, we have derived earlier as 1 over square root LC. Right? So then the wavelength we can define as 2 pi over beta. So beta value we know as omega square root LC. So using that we can find the lambda value if we know the value of beta, right? So as I said before, when the wave is propagating in high frequency, the series resistance value is negligible when compared to the inductance that is generated in the transmission line. Also, the conductance value is negligible when compared to the capacitance that is generated across the two conductors in the transmission line. So in high frequency wave transmissions, we can consider that this assumption, right? So when R is negligible when compared to L, J omega L, and when G is negligible when compared to J omega C, we take the same assumptions as before, that R is equal to 0, G is equal to 0, likewise, and so on, right? So I'm explaining this because like I mean, earlier we talked about the lossless transmission lines, right? Lossless transmission lines means there's no attenuation in the transmission line when the wave is propagating. So lossless means it's a very perfect condition, right? It's a very perfect condition. Lossless means very perfect condition, right? That means that the series resistance is 0, the conductance is 0, so everything is like very perfect. However, in actual scenario, we might actually have the effect of such resistance and conductance, right? Even so, right, when we are considering high frequency wave transmissions, right, we again uh, get the uh, condition that the series resistance value is considerably negligible or lower, considerably lower than the inductance, and the conductance is considerably lower than the capacitance, right? So that is why we are making this high frequency transmission scenario equal to the lossless transmission scenario, right? The same values are obtained for the parameters as in the case of lossless scenario for the case where we have the high frequency transmission of the wave propagation, right? So in microwave communications, in what frequency do we have our transmissions? In what range, as you think, right? What is the range? Can you put in the chat? What is the range of the frequency that is used for microwave transmissions, microwave communications? Right? I told multiple times in the class this. So we are talking about gigahertz range of uh, communication, right? So we are talking about frequency in the gigahertz range. That means a very high frequency range. So in that range, we can consider this assumption as a valid assumption, right? So because of that, we based on this assumption, and based on that, we are taking these parameter values in these equation formats, right? So then uh, we have to consider about the characteristic impedance, right? So the characteristic impedance I mentioned to you earlier, it gives us the notion about how much of energy or power we can transfer from one point to another point in the transmission line, right? So for an efficient maximum power to be transferred, the characteristic impedance of the line must be considered, and also it must match with the impedance of the line, right? So we need to take into consideration about the impedance of the load and impedance of the transmission line when we are uh, designing a transmission line circuit, I mean transmission line, and when we are connecting it to a certain load. In order for us to do the maximum power transfer from our transmission line, right, we are giving some power, we are inputting, we are feeding some voltage to the transmission line, and the voltage and current waves are generated, right? So those voltage and current waves must be transferred with maximum, uh, the maximum of those voltage and currents must be transferred to the load, right? So in order for us to do that, we need to consider something such as impedance matching, right? That means like we can transfer the maximum energy to the load when the load impedance is equal to the transmission line characteristic impedance. right? So that is what is said here. So therefore, uh, the characteristic impedance is important for us in order to decide like to what kind of a load we can do the maximum transfer of energy, and also if we are going to do the maximum transfer of energy, how can we do it, what type of a circuit must be used, maybe between the transmission line and the load, or else what kind of methods can we use to match the impedance between the transmission line and the load impedance, right? So therefore, characteristic impedance is vitally important when we are matching the load or matching the transmission line to the load, right? So we need to do impedance matching to transfer maximum energy to the load. So last time we derived these equations of Z naught, right? Z naught depicts the characteristic impedance of the line, and it is equal to minus V naught minus over I naught minus when we are considering the backward wave, which is reflected back from the load towards the input source direction, and it is equal to the plus magnitudes of the voltage and current ratio when we are considering the forward wave components, right? Apart from that, we also derive that it is also equal to R plus j omega L divided by G plus j omega C over square root, right? So we can take both these equations into consideration when we are calculating the Z naught value. In the lossless case, we only have L over C square root as the Z naught, right? So, as I said before, like one of the main goals of the transmission lines is to give maximum power transfer to the load, right? So if we consider a certain load is connected, ZL, uh, to a transmission line, right? There's a transmission line. This is the transmission line. At the end of the transmission line, we have a connecting wire, and there's a impedance in here, right? So in these types of circuits, please note that the total resistance after the transmission line, the total resistance, including the conducting wires and the impedance, are all lumped inside this impedance ZL, right? So after the transmission line, the total impedance is shown by ZL. So this includes the impedance in the conducting wires and the impedance of the load. So all the sum of those impedance are lumped into this component ZL. And then we are considering that the current across the this ZL impedance is IL, and the voltage across the ZL is VL. So we have we have denoted our voltages and currents across the transmission lines using these two equations in the previous lessons. So we can use these two equations, and we are now going to find out like what is the amount of reflection that can happen when a certain load ZL is connected to the end of this transmission line. What is the amount of reflection that can happen when we are connecting a certain load at the end of a transmission line. So we want to find out the reflection, like the magnitude of the reflection that can happen in the transmission line. So when we connect to another load. So when we want to find that, we want to first find out uh, the uh, the reflection coefficient, right? So in order to find the reflection coefficient, that means the ratio of the reflected wave over the incident wave, we need to first find out the uh, the uh, we need to first find out the relationship between the input or incident waves and reflected waves. And so we are going to we are going to form a relationship between the impedances in the line and the voltages in the line, right? So in order for us to do that, we are going to uh, take the ratio we are going to take the ratio of voltage and current in the line, and then we are going to represent all the uh, voltages and currents in terms of we are going to give parameters, different parameter called reflection coefficient to the ratio between the incident voltage wave and the reflected wave, and reflected wave over incident wave as the reflection coefficient, and we are going to replace these equations such that we can find out what is the reflection coefficient of this uh, transmission line at a certain location in the transmission line. So in order to do that, we take the voltage and current equations in the line, and then we try to represent them using the impedance values. So therefore, we convert the current equation uh, into voltage over impedance values, right? So in here, I naught plus, I naught plus, I naught plus value you can find using this first equation, right? We can write I naught plus as V naught plus divided by Z naught, right? And then we can put that V naught plus over Z naught into this position instead of I naught plus. Similarly, using this fraction, we can take that I naught minus is equal to minus V naught minus over Z naught, right? And then we know that the load or the impedance of the load is equal to the voltage at the load divided by the voltage at the current at the load. So in order for us to find the voltage at the load, we have to substitute Z equals 0 in these equations, right? By substituting Z equals 0, we can get that the voltage at the load is equal to V naught plus plus V naught minus, because e to the minus j beta Z is going to be equal to 1, right? Because Z equals 0 gives the cos 0 plus j sine 0, right? That equals e to the uh, e to the j, so we can find the value of that as 1, right? So we can the e to the minus j beta z will be equal to 1 in that scenario when z is equal to 0, right? E to the 0 is 1, right? So because of that, we can write VL is equal to V naught plus plus V naught minus. And then we have the situation of the IL. IL also same thing, e to the minus 0. E to the 0 is going to be 1, right? So because of that, we can substitute 1 for each of the exponential terms, and we are left over with this with these expressions. And so current is V naught plus plus V naught minus, and the voltage is V naught plus plus V naught minus, and then current is 1 over Z naught within brackets V naught plus minus V naught minus. By simplifying this, we can get this kind of equation, and then we next we consider this reflection coefficient, right? We denote the reflection coefficient as tau L. The tau L is equal to V naught minus divided by V naught plus. So V naught minus over V naught plus, we try to form in the previous equation that we got here. So in here we have V naught minus on top. We can divide all the terms in this fraction by V naught plus. By dividing all the terms by V naught plus, we can get that 1 plus V naught minus over V naught plus divide by 1 minus V naught minus divide by V naught plus. So substituting tau L into this ratio, we can get that 1 plus tau L divided by 1 minus tau L is equal to the ZL, right? So we have now found this equation, which is a simplification of the previous equation regarding the impedance of the load and the characteristic impedance of the line. Now we know, like using the characteristic impedance of the line and the load impedance, we can try to find the reflection coefficient value, right? If we know this Z naught and ZL, we can find the tau L, right? Tau L gives us how much of voltage is reflected back when a certain voltage is uh, input to the line, right? So at the load point, right? When we are considering the load point, when we are giving a certain voltage V naught plus, how much of that voltage is reflected back, right? That is V naught minus. That ratio is giving the reflection coefficient at this point. At the load end, we can find the reflection coefficient as this using this equation. Say if we know these values for these impedances, we can quickly find the value of ZL, right? And if the ZL is a complex impedance, that means it contains not only the resistance but inductance and capacitance, then this ZL value is going to be a complex value. If it is a complex value, then the tau L is also going to be resulted in a complex value. So we can represent the tau L in a standard notation as its magnitude into e to the j theta. That means we can denote this tau L as a polar form, as the phasor form, right? So in here, the theta, we must remember that it is minus 2 beta L, right? So beta in here is the phase constant, right? The phase constant that we considered earlier. So beta we can represent as 2 phi over lambda, right? So we will get into that a little later. So, right. So, uh, so transmission lines, as I said before, in here we can have different loads at the end of the transmission line, right? So sometimes we can have an open circuit at the end of the transmission line. That means ZL is going to be 0. Sorry, ZL is going to be infinity, right? If it is an open circuit, that means there's no current flowing through this impedance, right? That means the impedance must be infinity. Only then there's no current flowing across the two conductors. Then the open circuit condition is considered. So when we have such kind of special occasions, we can see some patterns in the transmission line uh, with in terms of impedance, for example. So we will take such special conditions or special loads at the end of the transmission line uh, connected such that we can observe the patterns in the transmission line. So in the case where we have ZL is equal to Z naught, right? The characteristic impedance is equal to ZL, then we have tau L equal to 0, right? So that happens because, right, we earlier derived the equation that, right, sorry, we derived this equation called ZL minus Z naught divided by ZL plus Z naught. In there, if the ZL is equal to Z naught, the value of tau L is going to be 0, right? That means like if we match or if we make the characteristic impedance equal to the load impedance, then the reflection coefficient is going to be 0. That means there's no reflection occurring at the end of the transmission line, right? So, so that is what we are trying to achieve in our transmission lines. We are going to transfer the maximum power to our load, and we don't want any reflection back. So we want to reduce the reflection. So in order to achieve that, we need to have ZL equal to Z0, Z naught. And at that point, tau L is going to be 0. And then another case that can happen is that ZL is considerably higher than Z naught. That means ZL reaches, for example, infinity. It reaches infinity, then it is very large when compared to the characteristic impedance Z naught, right? So in that case, we have an open circuit. situation, right? There's no current that is flowing across an impedance with infinite value, right? So when we have that situation, we have the open circuit. Tau L will be 1 at that time, because in this situation, we have infinity. And then since we can't do calculations with infinity, we need to divide both the numerator and the denominator by ZL. And then we can substitute the infinity for the ZL. So once we substitute infinity, right, for ZL, we can uh, we can uh, we can get the value of tau L as +1, right? So I hope you can understand that. So ZL minus Z naught divided by Z L plus Z naught is the reflection coefficient, right? So the reflection coefficient, right? If we want to find the reflection coefficient when the ZL is infinity, then we can't divide infinity by infinity, right? I hope you understand that. So in mathematics, there are many non-defined expressions, right? So we can't divide infinity by infinity, right? We can't divide infinity by 0. Likewise, we have certain rules, right? In order for us to do the calculation that we want, we are just going to do this trick where we are going to divide the all the terms in the numerator and in the denominator by ZL. Then we can easily compute the value of tau L without, you know, uh, without doing any uh, errors or doing any logical errors, right? So we can now get, when we equate ZL to infinity, we are left with 1 minus 0 divided by 1 minus 0, sorry, 1 plus 0. So it will be equal to 1. So tau L is equal to 1 when there's an open circuit at the transmission line end, right? Tau L is equal to +1 when it is open circuited, right? And then once we have the next condition, we have the short circuited line, right? So in here, we consider the situation where we have the open circuit situation where the ZL is infinity. And now we are going to consider the short circuit condition where we have the short circuit uh, configuration where we have the ZL equal to 0. Right? ZL is equal to 0. There's no impedance in here. So ZL equal to 0 means that tau L, once we take tau L, it is going to be 0 minus Z naught divided by 0 plus Z naught. In that case, the value of tau is going to be -1. Right? So in short circuit conditions, the tau L value is going to be -1. Right? So we need to use these conditions when we want to find out the values of voltage and currents and impedances along the transmission line. Right? So we can represent the voltage along the transmission line using the tau L, and in that case we can represent the we can represent our tau L based on the condition open circuit or short circuit, and by using that we can find the voltages and currents. So another important thing is that now we have considered about open circuit, short circuit, and no reflection conditions, but we also need to consider uh, a situation where there's no such special case, right? For any standard, any general case, we need to find the input impedance of the transmission line at any location in the transmission line, right? So in that case, we can find the input impedance by taking the ratio of the voltage and current at any location in the line, right? So the voltage and current at any location in the line, we can represent using these two equations, right? So in here, I have done a small change than the ones before, right? In the previous lecture, we denoted this using our V naught minus value, right? So in here, we have that in terms of tau L, right? So as you can remember, we can represent um, our our sorry, where is this? So we can represent our V naught minus in terms of tau L into V naught plus. Same thing with the uh, current as well. You can represent the current using tau L and I naught plus. So anyway, we can take this into consideration, right? We can take into consideration that V naught minus is equal to tau L into V naught plus. So in that case, we have the situation where we can substitute that in here, right? Instead of V naught minus, we are substituting tau L into V naught plus, and then we are removing the effect of V naught minus in these equations. In both the equations, we are removing V naught minus, right? And then we are taking the ratio between these two, right? And then we can find out that the final equation is uh, can be written in this form, right? So I will give you that as a assignment to do. You can divide these two terms, and you can show that at any like any location L in the transmission line, we can denote the impedance using this expression, right? So in order to get the tan and cosine sine values, we need to convert this e to the j beta L term as cos beta L plus sine j sine beta L. Once you write in the sine and cos terms, you will be able to divide each term by cos beta L, and then you can take the tan beta L terms, right? So uh, apart from that, once you divide these two terms, this Vz minus L and Iz minus L, you can remove the effect of V naught plus, right, in the numerator and the denominator. And you are only left with Z naught, ZL and tau L, sorry, Z naught, ZL, beta L as variables, and then L, beta and L, right? So you if you want to like find any of these parameters, when you know all the other parameters, you can use this equation, right, to find the input impedance at a certain location L, right? So we are taking in here the Z equals minus L because we want to take an arbitrary location in the transmission line. So you will wonder why I'm taking minus L, right? Minus sign is because we are measuring the length from the load side towards the uh, input side, right? So we are measuring from Z naught up to the minus negative side of the transmission line. So because of that, any arbitrary point in the transmission line, which is on the left side of the Z 0 point, we can denote as minus L point. So any arbitrary point is just represented used as minus L. There's no other like meaning to that, just minus in the minus direction after a length of L. What is the value of voltage is given by this V Z equals minus L. And then what is the value of current is given by I Z equals minus L, right? So I hope you can understand that. So in any general point in the transmission line, we can denote the voltage and currents using these two equations, right? So using these two equations and taking the ratio between these two equations, you can find the Z in L equation. So that equation is given in here. I would like you to derive that equation as an assignment, right? So I hope that part is clear to you, what I have explained to you about these equations. If you have any questions regarding these equations, please let me know. Right? So, right? So earlier I have mentioned that we can consider three special cases. So under those three special cases, we can also find the input impedance of the transmission line using the equation that we derived earlier, right? So once we take into consideration that the tau L is equal to 0, right? In that location, the ZL is equal to Z naught, right? So uh, once we consider the case where ZL is equal to Z naught, we can also we can see that the final value of the Z in value is going to be equal to Z naught, right? So because the beta L, once we take into the value of tan beta L, it is going to be equal to 0, right? So it is because we are considering the situation that uh, we are having all these two, like the numerator and the denominator equal, right? So once we have the reflection equal to 0, at any location in the transmission line, the input impedance is going to be equal to the characteristic impedance of the line, right? I hope it is clear to you. In this equation, right, when we equate ZL equal to Z naught, we can see that both the numerator and the denominator are equal. If that is equal, we can we can make this fraction equal to 1. We can cancel out the numerator and denominator because they are equal. The fraction is equal to 1. So because of that, Z in at any point in the line, the input impedance is going to be equal to the characteristic impedance of the line, Z naught, right? That happens mainly because ZL is equal to Z naught, right? There's no effect from the load to the input impedance of the line, right? The input impedance of the line is only characterized by the characteristic impedance of the line. The load impedance does not affect the input impedance of the line at any point in the line, right? In the case where we have the input impedance and the load impedance equal to the characteristic impedance. So that is a matched case, right? So in matched case, we don't have effect from the load impedance on the input impedance of the line. That is very important because most of all the time we are trying to achieve this case where the reflection coefficient is equal to 0. That means we are going to reduce the reflection of the voltage and current waves back into the transmission line. We are trying to stop the reflection happening. So we are trying to achieve this point. Right? In this point, if we achieve this, we will be able to achieve the condition equal to the line. So this is the condition, ideal condition that we are trying to striving to achieve in a transmission line. And then we have the open circuit condition, right? Open circuit condition means tau L equal to +1. We have derived that earlier, right? Tau L equals to +1, right? We have derived that earlier where ZL goes to infinity, and then we can divide the both the terms by both the numerator denominator by ZL, and then we can get 1 over 1. That means tau L is equal to 1. So when it is open circuit, we can consider that ZL is infinity, right? In order for us to calculate that scenario, we need to do a trick. We need to divide each term by ZL, and then we need to substitute infinity after dividing each term by infinity, right? I hope you can understand. You can't just substitute infinity to both numerator and denominator and write infinity over infinity. It is a not defined term in mathematics. It's not defined. In order for it to make it defined, we need to divide each term by ZL. And then you can substitute ZL equals infinity, and ZL equals infinity. Once you have substitute that, you can make some term 0, and you are left with this term, right? So I will ask you to do in the assignment. I will ask you to derive these equations by using the input impedance equation. Using this equation, I will ask you to derive the input impedance of the line when the line is terminated under different conditions, right? Open circuit, short circuit, and matched case, right? So similarly, for the short circuit, you can get the input impedance value using this equation. Once you after simplifying the initial equation in here, right? By substituting that ZL is 0, you can get the final outcome, right? So in here, you can assume that ZL is 0 when you're comparing to Z node. Right? So by doing that assumption, you are left with ZL. Once you make it 0, you are left with only J Z node tan beta L divided by Z node. Right, so that this equation is left over, and by doing some by cancelling out these nodes, you can find this expression for as correct for the input impedance of the line at when it is short circuit, right? So one thing that is noted here is that the input impedance of the line is an imaginary value. It is given as a term in terms of J, right? J denotes complex number. Once J is there, you know that this term is a complex number. And then also impedance value when it is short circuit, right? So at each point in the line, transmission line, you have completely imaginary valued impedance along the transmission line when it is under these two conditions, right? So in the matched case, right, it is completely real if the characteristic impedance of the line is real. So most of the time, the characteristic impedance of the line is a real value. So for normal transmission lines, we consider that the characteristic input impedance is about 50 ohms. So 50 ohm is a real value, and it is used as the Z naught value in most cases, right? So we can use this result that we got for the input impedance and for the conditions under short circuit and open circuit to find the characteristic impedance, or Z naught, of a transmission line. So if we don't know the characteristic impedance of a transmission line, we can use this relationship to find the characteristic impedance. That means that for a situation where we have a like a microstrip line in a like a right, when we have a microstrip line that we are going to use for our for one of our applications, we are supplying a voltage at the uh, at the microstrip circuit. We are supplying some voltage, right? So in this situation, right, we can have a situation where we don't know the Z naught value of this transmission line, right? So in that case, in order to find the Z naught value of this transmission line, we can consider we can short circuit. So if we assume this is the ground plane, we can short circuit this ground plane and the top plane using some conductor that we directly connect between these two conductors. If this is the top conductor and this is the bottom conductor, we can connect the top and the bottom using a direct conductor line. So using that short circuit scenario, we can measure the impedance, the input impedance at this location of the line, at the feed point of the line. And then again, we can do the same, we can consider the same circuit, and we can we can make this open circuit. We can keep this as open circuit, and we can measure the impedance at this feeding point, right? Then we can use those values, the input impedance values we measured when it is short circuit, and the input impedance value we found using when it is open circuit, and use those values in the equation Z naught equals to square root of Z short circuit and Z open circuit to find the characteristic impedance of the transmission line, right? So Z naught value, although we take it as a certain value, sometimes it might not be that same value for the specific microstrip line we are considering. So in order to verify that Z naught value is the one that we are considering, right? That in order to verify the value of the Z naught, we can use this technique to find, we can use this experiment to find the Z naught value, right? We just need to find the input impedance of the transmission line when the end of the transmission line is short circuited and open circuit. And so this method can be used when we don't know the value of the characteristic impedance, right? Then we can consider also, right, that that Z in, as we considered earlier, it is a function of the imaginary number j, and then we have Z naught tan beta L as the function of the input impedance when the transmission line is short circuited at the end. So in here we can see that the input the impedance of the line when it is plotted against the length of the line, it is varying using in this pattern, right? One thing to notice is that once we are short circuiting at this end, we can observe an open circuit condition after lambda over 4 distance. Right? After lambda over 4 distance, this plot has an infinite impedance. Right? This plot is showing the impedance of the line. Right? So at the end of the transmission line, it is starting from this left end, and then it is 0 because it's a short circuit. Right? Once you are going a lambda over 4 distance, this input impedance is reaching infinity. Right? It means that that transmission line is reaching an open circuit condition at lambda over 4 distance. Right? After again, when we move lambda over 4 distance, we are reaching Z input impedance equal to 0 condition. That means a short circuit condition, right? And then so that means that after short circuit condition happens at the end of the transmission line, after lambda over 2 distance, the same short circuit condition occurs in the transmission line, and in between we have an open circuit condition happening at lambda over 4 distance, right? So then again, once we go up to like 3 lambda over 4 distance, we have this open circuit condition happening again, right? And then we have short circuit condition happening again. Likewise, we have a periodic short circuit or short circuit open circuit short circuit open circuit condition happening along the transmission line. It's a very important behavior to notice in a transmission line. Similarly, when we are doing the open circuit condition at the transmission line, same situation is happening. So at the open circuit end of the transmission line, we are seeing infinite impedance. And once we are moving a lambda over 4 distance, we are seeing a short circuit condition. That means impedance is equal to 0 condition. That means a short circuit is happening at the lambda over 4 distance away from the end of the transmission line. And then once it is short circuit, apart from that point onwards, once you are going lambda over 4 towards the power source, then again you are observing open circuit condition. So this periodic impedance pattern is seen in a transmission line. So we are considering a lossless transmission line. So this periodic impedance variation is seen in the lossless transmission line. So from that note, I will end today's class. If you have any questions, you can let me know.